Thank you for inviting me here, and thank you for coming. So today I will tell you about. Can everyone hear me? So today I will tell you a little bit about constraint satisfaction problems and hardness of approximating them. But before I tell you the results, I really want to focus on the main technical ingredient that will be used in the result, and which may be called an XOR lemma. And the study of this technique will be is an interesting math problem on its own. And an XOR lemma is something we can use to amplify the hardness of a k-player game. And here is what I mean by a k-player game. So here I'll just ask k questions to k players. These k questions are v1 to vk, and the judge wants to know the truth of these k statements or k questions. And the judge will choose these couple of questions from a collection M at random. Each player gets one question. The player does not know the answer the questions to the other players. They have to answer these questions independently. And after getting a Boolean answer from each player, a yes/no answer from the player, the judge now gets a reply, which is a KB string. And the judge will accept if this KB string satisfy a predicate, or it belongs to a predicate C. So think of this C as maybe the collection of all strings of even parity. Then the judge will accept if an even number of players reply 1. So the judge is checking whether an even number of statement is correct. Each v1 to vk is like a statement. So this is the setting of the game that we will consider. Actually, the judge will be more powerful. The judge can ask the negation of a question. Instead of asking whether a statement vi is true, the judge can ask whether a statement is false. But from the answers from the players, the judge can infer the truth of the statement. So the judge might sometimes ask the opposite of a question and negate the answers and check whether all these k statements are an even number of statements is correct. Oh, so yes, actually, that's a very good question. All k players, they know f sub I, so they can come up with the strategy beforehand. They know that they are going to play this game. They know this set M of questions that the judge will choose from. But they just don't know what is the random choice of the questions at when the game is actually played. What are the questions to other players? That they don't know. Other things are public. And so why do we study this game? As I will explain in a little moment, in the second half of this talk, we study this game because of its application to hardness for approximation. But I guess it's also a natural game to study on its own. So we will be talking about games like this, a k-player one-round game. And we really want to understand how you can amplify the hardness of this game, how to make this game harder for the players. So what do I mean by making a game harder? We want to reduce the acceptance probability of a game. Maybe the judge is forced to accept with probability at most 0.9. Even under the best strategy of the players. Even the players, before playing the game, they know they have come up with the best strategy for the game. And they know their goal is to maximize the acceptance probability of the judge, and still the judge can only accept with probability 0.9. From this game, can we create another game with much lower acceptance probability? Here, the acceptance probability is only over the random choice of the questions. that the judge chooses. And so this is the question. Here's a natural approach to amplify hardness. We play the game multiple times, but what we also still want to only ask. The judge only wants to ask one question. Only want to ask question at the same time to all the players. So what the judge can do is choose a number of questions beforehand and ask all of these questions to each player at the same time. The hope is that, and so for example, this is the idea behind parallel repetition. In parallel repetition, the judge will also get L bit string as the reply from the players, which is the answer to all the answers to all the questions. The hope is that the players has to answer all the questions simultaneously, and this will make them much harder to fool the judge. And the parallel repetition of a k-player game will also be a k-player game, but not of the same k-player game that we have seen in the previous slide. Because the reply from the players is not a yes/no answer, it's not Boolean. So in this talk, we will not look at parallel repetition. And instead, we want to consider another hardness amplification technique, which is taking XOR of this of a game. What do I mean by that? The judge will again choose. So an XOR is like a variant of parallel repetition. The judge will ask L questions at the same time, and the players is supposed to answer just one Boolean answer, which is the sum of answers to all the games. So here's the formal definition of taking the XOR of two games, M and M prime here. The judge pick one question tuple from the first game and another question tuple from the second game. The judge then asks, what is the truth of the first statement XOR with the truth of the second statement? Each player gives a reply, and the judge will does a check at the end. So we are going to study this technique to amplify hardness. Intuitively, if we start with a game where the judge can only accelerate probability at most 0.9, and we take the XOR of the same copy of the game, many copies of the same game, it seems that the players would to be able to answer the XOR of the questions in this repeated game, the players should answer all games correctly. The intuition is that has to answer all questions correctly. So the acceptance probability of the judge should decrease towards the value, the random assignment value. So in this case, the players don't have a better strategy to answer the judge questions other than given a random assignment. So this is what we expect to be true. So here, when I consider this statement, I don't even assume that C is close on XOR. But later on, I will assume that. So
the last strategy when
answer
both the questions correctly.
Will
it require C to be answered? It's fine.
So yes, you should think of C you should assume C is a proof to be close on the XOR. But when I post this statement here, you might even consider C as not as a group. So I'm just asking if the replies from the players will look more and more random as you play the same game many times and ask the players to answer the XOR of all the games. Something like that is true if K is 1 or 2 for one-player game and two-player game. You can prove that it is true. But I found it quite surprising that for free-player games and more, this statement is false. And there is a counterexample pointed out by Briette and others, known as the Marines game in the quantum player games literature. And this game is very simple. There are only 4 possible questions. It is a free-player game. You don't need to remember the details, but it is so simple that I just write it here. The judge will choose one of these questions, send these free bits to the free players, and expect the answers to be of this parity. What's so special about this game is, if you stare at it for a moment, you will realize that no matter what the players do, they can never force the judge to always accept. The judge can accept with probability at most 3/4. So there's no perfect strategy for the players. But surprisingly, there is a quantum strategy for this game using in some special kind of entangled states, GHZ states. And this quantum strategy implies that in the repeater games, there's also a perfect quantum strategy. And such a quantum strategy can be rounded to a non-trivial classical strategy, a non-trivial strategy in the usual sense. That is not random. And so an XOR lemma like this above would be false. And maybe I should pose a question here. Is examples like this, examples where you have where you can round this a quantum strategy using quantitative inequality, is this the only obstruction to an XOR lemma? If a game does not have perfect quantum strategy like this, will the value of the game goes to the random maximum value? If this is true, I think you can possibly reprove some inapproximability results about linear equations without using parallel repetition, but just using XOR. This is one interesting question. So we know that we cannot amplify the hardness we wish using XOR. So using a result like this. So what can we do to amplify hardness? In the second half of the talk, I will talk about hardness of approximation results. And here is the strategy that we will use eventually to amplify hardness. It is like we strengthen the assumption of our game. Instead of saying the value of the game is at most 0.9 to begin with, of a single game is at most 0.9 to begin with, and we will instead assume a stronger assumption on our basic game, and then we will use a weaker version of XOR lemma. That will be true, a weaker version of the XOR lemma. So we strengthen the assumption. We want to have a game where the reply of the first player is uncorrelated with the replies of the other players. Actually, the replies of the negation is uncorrelated. It's like one guy is spitting out a bit that is uncorrelated with the other bits from the replies of the other players. And we will use the observation that the correlation of the player's reply will only decrease if we take the XOR of the game. So in the second half of the talk, the strategy that we will use is we will create k different games where in each game a different player is chosen to be singled out, and we will make that player's reply to be uncorrelated with the replies of the other players. And then if we take the XOR of these k games, we will achieve a situation where all players' replies are uncorrelated with each other. And this means amplification of hardness. We make the game really, really much harder for the players. Note that, so in this situation, the players' replies are like uniformly random. And this is the strategy that we will use in the second half of the talk. Okay, I need to justify why is this observation true? Why is the replies from the players, why does the correlation always drops? It can never increase. The answer is very simple. If you know why, it's the same reason why when we do parallel repetition, the value of the game will never increase. The value of a repeated game in parallel repetition is at most the value of a single game. It's because to be able to play all the games in a parallel repetition, you need to be able to answer at least one game correctly. It is the idea behind this observation. So, all right, yeah. So this is the proof, but the intuition is just the same as what I told you, and so we want to apply the technique and XOR lemma to prove.
What is meant by correlation between?
Okay, so here you can think of the replies from the players as a KB string. Okay, yeah, maybe I should tell you a little bit more about this slide. We will look at the random KB string, which is the replies from the player after the negation by the judge. This is what the judge sees at the end of the game. This is what the judge sees at the end of a game. Right before the judge checks whether this is, the replies satisfy predicate C. And we want to say that this random variable, a random KB string, will be uniformly random in after we take XOR. So how do you say that it is uniform? Random variable is random KB string is uniformly random. We look at the Fourier coefficients of this. We look at the Fourier coefficient of this random variable. A random KB string is uniformly random if all the non-trivial Fourier coefficients are 0. So we need to bound the Fourier coefficients of this random variable, of this random KB string. And that's why we look at the Fourier coefficient at chi for this random KB string, the outcome at the end of the game, when the judge wants to check whether this KB string belongs to a predicate C. And so we need to bound all the non-trivial Fourier coefficients by something very small, something close to 0. And the observation I claimed earlier is exactly that this Fourier coefficient at chi of a XOR game is at most the same Fourier coefficient for a single game before taking XOR. And intuitively, it means if one guy's replies is independent of other guy's reply, then after taking XOR, the same guy's reply will also be independent of other guy's reply. Any other questions? So this is the technique that we are going to use, and we will apply it to some Hardness approximation results. And we want to apply it to this problem, max CSP, maximum constraint satisfaction problem. So this is in this problem we are given a collection of constraints. We want to satisfy the maximum fraction of these constraints. There are two famous examples: max free XOR and max free set. In max free XOR, we have linear equations with 3 variables per equation. We want to find a Boolean assignment, 0-1 assignment to satisfy the maximum fraction of equations. Another example of max CSP is max free set. We are given a formula in conjunctive normal form. We want to find a truth assignment to satisfy the maximum fraction of clauses. And one interesting feature about these two CSPs I've shown you is that these two CSPs are approximation resistant. It means that even if the instance have an almost satisfying have an almost perfect strategy, have an assignment to satisfy almost all constraints, it is still hard to find an assignment that is just slightly better than the random assignment. So we can always, a random assignment value here means what fraction of constraints you will satisfy in expectation if you just output a random assignment. It will be half for linear equations and 7/8 for max free set. So in a similar work by Hustad, we know that max free XOR and max free set are approximation resistant. And one natural question to ask is what CSPs will be approximation resistant? In this workshop, you will see a lot more recent development on this question. And the Hardness result I'm going to tell you says that a CSP is approximation resistant if it satisfies a certain technical condition. I call pairwise uniform subgroup here. And so this condition will make a CSP very hard to approximate. So hard that you cannot hope to have a non-trivial approximation algorithm to beat the random assignment. And so I'm going to tell you this result to give you a sketch of the proof of this result using the technique of XOR I showed you earlier. And for now, first, I need to define the problem more formally. So we are going to consider constraint satisfaction problem, where all constraints will involve the same number k of variables. K is free in the max free XOR max free set, and each constraint accepts the same collection of local assignments. So for example, if the predicate C is the set of all strings of even parity, then we get the max CSP problem is exactly max free XOR I showed you earlier. Another example, if the predicate is all strings except the free zeros, the CSP is max free set. And note that each constraint is allowed to depend on k literals, not just variables. So the literals can be positive or negative. And we want this feature because, for example, in these literals somehow correspond to the right-hand side of linear equations in max free XOR. And clearly, a random assignment will specify this fraction of constraints, the size of C over 2 to the k fraction of constraints in expectation. And okay, and here's what is known about such CSPs. So here I have a big ellipse, and the red region represents some CSPs that we note are approximation resistant based on previous work before 2012. And it's a small fraction of CSPs have been classified as approximation resistant. I believe not even a constant fraction of CSPs were known to be approximation resistant. And there's an interesting work and that shows a lot more CSPs are approximation resistant. This work by Austrian and Morsel says that if we have a predicate, if a CSP is given by a predicate C that is pairwise uniform, then the CSP is approximation resistant. What does it mean to be pairwise uniform? It means that if you choose a random k-bit string from C uniformly at random and look at two coordinates of the string you choose, the marginal distribution on the two coordinates is uniform. Anything that satisfies this condition is called pairwise uniform. For example, if C is the collection of all strings of even parities, such a collection C is pairwise uniform. Because if you pick an even parity string at random and look at two coordinates, the marginal distribution is uniform. So in particular, Austrian and Morsel reproves the result of Hofstad earlier. Except there's a catch. Austrian and Moser results requires this unique a complexity assumption known as the unique games conjecture, and we do not know if it's true or not. So the Hardness result I'm going to tell you says that we can prove a very similar result if we assume the set C is not just pairwise uniform, but also a subgroup of C2 to the K. Then the CSP you construct from those predicates will be approximation resistant. Which one?
Three set, three clauses.
Oh, very good. That's a very good point. I should point it out. So, max reset is not pairwise uniform under this definition. But both Austrian result and this result here works if the predicate C contains another subset that is pairwise uniform. So, for example, max free set will contain this max free set here contains the first example. Well, contains all strings of odd priorities rather than even priorities, and which makes max reset approximation resistant. And it's a very good point. Yeah, thanks for pointing out.
It doesn't even have to be a sub.
That's also true. Yeah, I am lying here because Austrian and Moser result is more general than what is stated here. Yes. Thank you. So with and our result does not assume the complexity assumption, the unique games conjecture. So it means that by an earlier result of Hofstad, this actually means that almost all CSPs will be approximation resistant. For a typical constraint satisfaction problem of this form, you do not expect to beat the random assignment. Random assignment is the best algorithm you can come up with. And this is the main result that I'm going to tell you in a moment. Here are two corollaries of our main result. It shows that if we have a CSP instance where each constraint depends on exactly K variables, this special case is called max K CSP, then you cannot hope to approximate better than, you cannot hope to satisfy more than K over 2 to the K fraction of constraints if almost satisfiable. And this just follows from our result about pairwise uniform predicate. If you plug in a predicate given by Semiransky and Trevisan, they came up with this predicate, which is essentially Hardness code, and this Hardness code has size almost 2K, and you plug it into our theorem, it shows that you cannot approximate better than K over 2 to the K, and this matches the best algorithm we know up to constant factor. And similarly, even though this talk will focus only on the Boolean case, everything I said has an analogous version in the non-Boolean setting. And so you also get the optimal Hardness result for CSPs when players' reply are not Boolean. And there are a number of other applications also. So for the remainder of this talk, I will sketch a proof of this main result. If we have predicate which is a pairwise uniform subgroup, then the CSP you get is approximation resistant. And as a reminder, pairwise uniform, you should think of this C as the set of strings of even parity. Okay, the high-level idea of the proof is, well, we want to prove an NP-Hardness result, so we have to start the reduction from free set and then to our max CSP instance. And one good starting point is this label cover problem, which is known to be NP-hard to approximate with a very large hardness gap. And we will reduce this to our max CSP instance. I'm going to tell you what label cover is in 2 slides. So don't worry if you don't know what it is. But our strategy is to prove a label cover instance, a certain CSP, where the players have perfect strategy. We want to map such an instance into an instance of our CSP instance with good value. And we also want to map a label cover instance of bad value into our CSP instance where the players don't have non-trivial strategy. And this is the plan. We will actually do the reduction in 2 steps. The first step, composition, something I will tell you in a moment. And the second step is this XOR step, this XOR operational that I introduced earlier. And here it is crucial that in the second step, we will, in the step in the middle, we will get a CSP instance where players have an almost perfect strategy. We will map it to another CSP instance with almost perfect strategy. It is crucial that C is a subgroup, so the player's answer will still stay in the subgroup if they have, yes. Okay, so we want to prove a hardness or approximation result about CSPs and how is this related to K-player games I told you earlier. So actually, a K-player game is just another way of viewing a CSP instance. A K-player game, we will think of a CSP instance as a K-player game where the K-players try to convince a judge that the CSP instance is satisfiable. So the judge is unconvinced. What can the judge do? The judge pick a random constraint from our CSP instance and ask for the assignments to the K variables in the constraint from K players. Then the players can just tell the judge, okay, here's what I will assign to the first variable in the constraint, what I will assign to the last variable in the constraint. Based on these answers, and together with the literals on the constraint, the judge can check whether the player's answer, the replies from the players, will satisfy the predicate. And remember, the predicate is satisfied if the assignment on the clause after negation belongs to this subset C. So a K-player game is just another way of viewing constraint satisfaction problems. So, and to prove hardness results about CSPs, we just need to show that the players don't have a good strategy to play a game. We are going to reduce to max CSP instance from this label cover problem that I'm going to tell you now. So a label cover problem is like it's a similar game, except it's played between 2 players and a judge, not K players. And these 2 parties try to convince a judge that a certain CSP instance is satisfiable. This CSP instance will have large RLT. Each constraint will depend on a large number of variables. Even though I draw, in this example, each constraint depends on only 3 variables. In reality, it will depend on a large number of variables. The player's replies also will not be Boolean. And in this game, the label cover game, the judge wants to know whether this instance is satisfiable. So the judge pick a clause, say this red clause at random, and then a variable from the clause, say this blue variable, and ask for assignments from the 2 parties. One party will answer local assignments to all variables in this clause, this red clause. Another party will answer the assignments to the variable. And the judge can check whether the 2 players are honest by checking whether the assignments agree as the variable. And this label cover game, it turns out that there is a huge gap in the winning probability, in the acceptance probability of a judge. It is NP-hard to decide whether the clause player and the variable player have a strategy that always satisfies the judge, or if no matter what the 2 parties do, the judge will accept a probability close to 0. And And this follows by the PCB theorem and parallel repetition theorem. So the upshot is there's a huge gap in acceptance probability of this game. And we are going to take advantage of this gap to transform it into a huge hardness gap in our CSP instance. And we would transform this game in a composition step that was, I think, pioneered by Hosted. So we want to transform a label cover game into a key player game. Even though the players are given Boolean replies, but they are actually playing the label cover game in disguise. And so we hope to, this way, we hope to translate the huge hardness gap of label cover into a hardness gap of our CSP instance. So here is how we translate the game. Now key players want to convince a judge that there's a satisfying assignment to a CSP instance L, the same CSP instance in the label cover instance. The judge start the game by picking a random clause and a random variable from the CSP instance L, just like label cover. The judge wants to know the satisfying assignment to the clause and to the variable. But instead of asking for the assignment to the clause and an assignment to a variable from the key players, the judge cannot do that because in this max CSP game, we want players' reply to be Boolean, to be just a yes/no answer. So what we do is we will also pick a subset Z1 of satisfying assignment on this clause and ask the first player, is the satisfying assignment to the clause, does it belong to this subset Z1? Now the players can just give a Boolean answer, yes or no. That will be encoding some information about the satisfying assignment to the clause. Likewise, for some of the players, the judge will pick a variable and a set of satisfying assignment to the variables and ask, is the satisfying assignment to the variables, does it belong to this subset? So the upshot is the players' replies are all Boolean, and now we get the same KPI game as we saw before. And so this is a composition step. Here's something that I didn't tell you, how the choice of the ZIs, how do we choose that, and how do we choose the negations BI to BK. But I won't go too much into details about them. They are chosen according to something called the Taylor test, known as Taylor test in the literature. Here I will just say one word. What goes wrong if we just do a composition without the XOR step that we introduced earlier? The problem is each player. The question to each player is a clause plus a set of variables on a set of satisfying assignment, or a variables plus a set of satisfying assignments. So some players will share the same clause, and other players will share the same variables. This shared information will allow the players to give an assignment that will not be uniformly random, no matter what label cover instance you begin with. So this was why a simple reduction using just composition will not work, and we need the XOR step. Okay, I will quickly finish up. I will quickly tell you the remaining ideas that go into the composition step. The second step of XOR is just what I told you. So in the composition step, we want to map a label cover instance to a CSP instance where one player's replies is completely uncorrelated with other player's reply after negation. The condition here just means one player's reply is independent of other player's reply. And here we will use standard tools from Hardness Approximation to analyze the composition step. And the tool we use will show that if the player's replies are if the J player's reply is somewhat correlated with other player's reply, then there must be somewhat close to an honest strategy of answering whether the satisfying assignment to a clause is whether this subset of assignments the satisfying assignment to a clause belongs to a certain subset. And to analyze these results, we will use is here where we use the pairwise uniformity condition on the constraint, and we will use a powerful tool known as invariance principle. And what is the invariance principle? In invariance principle, it's a generalization of the central limit theorem. In central limit theorem, we have n independent plus or minus 1 random variables x1 to xn. If we take the sum of them and scale down by root n, the distribution is just a Gaussian, standard Gaussian G. But the standard Gaussian is also the same thing as sum of n independent standard Gaussians scaled by the same value, 1 over root n. So the invariance principle developed by many people says that it generalizes this fact. It says that if we have a low degree polynomial that does not depend too heavily on any single coordinate, and if we plug in plus or minus 1 independent plus or minus 1 speeds versus independent standard Gaussians, the distribution we get after applying the polynomial will be similar. So central limit theorem is a special case where the polynomial is summing all the inputs and scaled down by some factor. And the invariance principle is actually more general, and it applies whenever, not just to plus minus 1 variables versus Gaussian. It applies whenever the variables have matching first and second moments. And it is here, I won't go into details, but it is here where we use the pairwise uniform condition to argue that we will create two variables that have matching moments. And then we can apply the invariance principle to finish the proof, to say that our composition state is sound. Okay, that's the invariance principle, and I think I should almost wrap up now. I won't go through the details of why we have mentioned two moments. Let me finish up by posing a few open problems. So, due to technical reasons, the max CSP instance that we produce at the end will not have a perfectly satisfiable strategy. So this does not say anything about hardness of approximating max CSPs if the CSP instance is satisfiable to begin with. And a natural question is, what is the hardness of approximating CSP when they are satisfiable? It seems that substantially newer ideas are needed to answer this question. And another question I mentioned earlier is the coordinate inequality and only obstruction to this XOR step. And finally, I think it would be of interest to de-randomize the XOR step. Right now, if you take the XOR of an instance, it will blow up the size of the instance by a lot. Can you work around it? Can you do a de-randomized version of XOR and still achieve a similar soundness? And that's it. Thank you.
So in the second step, I mean, do you imagine there's some, like maybe in the next talk, relaxation of the game, which does tensorize, and relaxation is given by this kind of multilinear?
I tried thinking in that direction to prove XOR lemma. So the analysis I show you here do not go through that. Do not do relaxation. And you're asking whether you can do relaxation and do the second step. I don't know what would be the right relaxation. Maybe it's possible to find a relaxation and then prove XOR lemma whenever coordinate inequality does not apply. I mean, yeah, whenever you don't have perfect quantum strategy. That might be one way to go to prove a true XOR lemma.
Like, I mean, the most what if it's just the quantum value?
Oh, I see. Are you asking maybe what is the quantum value of the game here, or?
just I mean, I have no idea, but does, I mean, the net, I mean, is it just, what if could the quantum value tensorize?
With the, okay. I believe even that is not known. I believe even that fact is not known. Yeah, whether the quantum value tensorize, and also there are some technical details there. Quantum people, they have considered whether quantum value tensorize. Maybe some people will consider whether quantum value tensorize. Some people will consider whether quantum value using only this restricted class of correlations, restricted class of entangled states tensorize, and I think both forms are probably open. Whether when the players are allowed arbitrary quantum values, and the players are allowed only this restricted class of entangled states, the value of the quantum game will it tensorize? I think both are open. Yeah.
I guess you cannot hope to get from 0.9. You eventually it should converge to coordinate of CO2 to the k. So you should only look at XOR games so that you want to get to 0 instead of getting to some.
Yes. Yeah. Right. Yeah. We will. Yeah. Certainly.
So you would want to show this XOR lemma only for XOR games.
Right. So by XOR games, do you mean the explicit predicate of?
Yeah, the predicate is an XOR.
It's an XOR.
Because that means you go to 0 instead of going to some.
I suppose
0 correlation.
Yes. I see. Yes. Well, yeah, but maybe yeah. I see. Yeah, that's right. Or maybe you can hope for a stronger version where you want all Fourier coefficients to go to 0, all non-trivial Fourier coefficients to go to 0, starting with the assumption that all Fourier coefficients are bounded away from 1. You can also ask those kind of questions. So not necessarily a XOR game. Yeah.
So you thought a lot about this question. You know, if now you have one small Fourier. I mean, each Fourier coefficient is small in one of the games, right?
Yes. And
just that they were just smaller than 1. Did you try?
I believe so. I think it should be possible to prove that after the composition step, the quantum value of the game should be bounded away from 1. I think you might be able to prove that. I mean, at least with these GHC states, the quantum value when the players can only use GHC states, the value I think you can prove that is bounded away from 1. But then I don't know how to carry out the second step to prove a true XOR lemma to boost the hardness. I spent some time on it and I don't know how to prove that.
So you're addressing a very specific type of constraint families, right?
Yes.
Because you have just a single constraint.
Yes.
And actually, well, it's not exactly that you have a single constraint. You have a single constraint that shift, like you.
Yes, also allows literals. Yeah.
Yeah. And so, like, is there like a chance to address like any other type of constraint families? Like, for instance, when you really have a single constraint, or
but maybe no literals or.
I beg your pardon.
But no literals.
But no literals, for instance, or like a logic, or like other types of constraint families.
So first, this is a very natural question to go, natural direction to go, and so the technique here is really, I think you can, the general situation I think will be quite complicated. Yeah, the technique here would not be able to address the general situation, like what you said, and even removing the literals. The technique here will not work. Yeah, I think substantially new ideas is needed to answer those questions. And the reason is because we start the reduction from label cover, and label cover form is very restrictive, and
break now, and the next talk is at 10:15.